All right, so as you guys can see, this week we're going to be talking about mesh loop analysis. This is one of my more favorite approaches to solving circuits. Mesh does have its limitations. If you're missing some information, it can be hard to gather that. You kind of need to have the same information when you're solving for mesh, but you know, if you have to, you can always 7-eye something real quick and then throw it into a mesh to solve everything. Out of all the methods, though, mesh is my favorite. I used to really hate it, but honestly, you won't have to use Thevenin a lot. The biggest thing is if something burns up and you don't know what it was, if you have a measurement previous to that where that component was, that measuring a current or a voltage or something like that, it's easy to replace it. I've used it once in a while because we couldn't find schematics, we couldn't find replacement parts, and so we troubleshot the circuit. We did find a picture of the circuit, the schematic what it was supposed to be, but it was still missing some of the information. We did find a current that we had, and that's what we were able to troubleshoot it back. So I've used it once in the field, but it's more of the way of thinking about things to get things to work. So is the idea behind this. So mesh, we're going to refer to it as mesh. It's a method of solving electronic circuits through simple analysis using mesh currents, which we'll talk about what those are and how to use them. And we are making a starting assumption of what direction these currents are going. So the nice thing is whether or not our assumption is correct, it still works out in the end to be the same. We will just be given answers if our current was either positive or negative. If it's negative when we're done, our assumption was incorrect. That's all it means, which is nice because we still get the correct answer. It just may be going a different direction of what we were thinking. So all of our assumptions, they're going to be clarified and corrected at the end. The final values will dictate actual current directions as well. And then with those, we can solve the rest of the values for our circuit. So basically what we're going to do for mesh is we need to identify our starting meshes. So we'll have our circuit, we're going to identify the meshes. And one thing that we're going to do is we're going to assume all of our currents are going to go in a clockwise manner to start with. Whether or not that's how the current is actually going to flow, that's how we're going to assume. Then that way we use the same process over and over again to the repetition. That's how all the quizzes are going to be handled. Is they're going to be assuming that we're doing clockwise directions. Then as we go, we're going to use the Kirchhoff voltage loop. That's how we'll get these equations. And then we're going to basically use simultaneous equations to solve these guys. That's why last week we were running through the basics of simultaneous equations. Remembering that we have to have one equation for each variable. So if we have 3 variables we're trying to solve for, we have to have 3 equations. After we get these currents that are found out, any of them that come out negative, we just simply reverse their direction on our original drawing, and that will show actual direction. We may have some where we have currents opposing. When we come to the final voltages through those, we'll take those into account and kind of use a little bit of superposition to cancel each other out. And then we'll solve for the total voltage drops, and we'll double check it using Kirchhoff's voltage loops. Like I said, that's a lot of steps that we're going to do. We'll go through each of these individually and show you how these all work. So the first circuit we're going to start out very simple. So we're going to start with 30 volts. This is V1. We have R1 is 330 ohms. R2 is 170 ohms. And R3 is 330 ohms. Now we could go through and we could solve this circuit really easy. It's just a simple series parallel circuit. We take those 2 guys in parallel, add it to this, and we're going to solve all these values. But what we're looking for is we want to know our current total, the voltage drop across R1. We want to know the current through R2, the voltage through R2, the current through R3, the voltage of R3, and then the powers. A lot of the same information that we're solving for every circuit that we look for, or that we work on. All right, give everybody a chance to write that down. So one of the things we're going to be looking for is when we create these guys, we have to kind of take an abstract look at these circuits. The reason it's called mesh is think of when you're looking through a screen. What we have in the screen is the wires, our resistors, our connections. What we're interested in is the spaces in between those. So in this case, we're going to have two currents, two loops that we're going to focus on. So the first one, we'll label this one as loop A. We'll label this one as loop B. So again, the first step is we identify how many meshes we're going to have, how many loops. We're going to establish a direction of current. So in this case, remember, we're always going to establish it as clockwise, whether or not that's what actually happens. And in this instance, we're assuming conventional electron flow. Okay, conventional current. We're flowing from positive to negative. So just keep that in mind. Now, the next step we need to do is we need to create our equations for these loops. So we're going to start with the red one for loop A. So these are going to be, like I said, the Kirchhoff voltage loops, what we're looking for. So we're going to start in one spot and wrap around and write down what we get to get these. So the first thing we have is a minus 30. Next thing we have is a plus R1 times IA, because that's how we get the voltage for this guy. It's the resistance of 1 times whatever current this is going to be. Then we come to this next component. How are we going to get this voltage drop? What are your guys' thoughts? How do we get voltage? Resistance times current. Okay. In this case, we have two loops going through this one component. So we have to look at what direction we have going. So we have the red current coming down. We have the green current going up. So we're going to get one voltage induced by this A current. We're going to get another voltage induced by this B current. And what are going to happen with those currents? They're not necessarily going to be zero. They're going to superimpose over each other. They're going to cancel each other out. Okay? So in this case, we're going from the point of view of A, because that's the loop we're on. So we're going to add R3 times IA. Then we're going to subtract R3 times IB. That way we're taking into account both of these currents and both of these voltages that are going to be induced across R3. And then we have nothing else. We set that equal to 0. So that is our first loop. Does that make sense?
So the current loop is, you mean like the total current of the current flow going through that one loop?
Yes.
So if we go current B, it means the two resistors in that current.
Correct.
Okay. Making sure I got that right.
Yep. So we are just looking at this loop. That's it. Nothing more, nothing less. What are all the voltages? What are all the components that this current is going to have an effect on? So again, we start at any point and we just make our Kirchhoff's voltage loop. So we have the negative 30. Then we're going to run into the positive R1 times IA plus R3 times IA, and then we're going to subtract. So because we have this current that's opposing it, we could have made the assumption that this current was going down. We could have. But either way, we want to make sure everything clockwise just to get a consistency. We subtract off the voltage drop of this loop. We set everything equal to 0. So now we need to solve for the second loop. This is doing mesh. This comes in handy if you have multiple colors, because then you can keep track of what's what really, really easy. You'll see me switching colors a lot with this because that's, like I said, that's the way I see it. It'll keep track of everything when we're jumping back and forth trying to figure out which one is which. So our loop B, loop B, we want to do Kirchhoff's voltage loop as well. So if we start here, and based on this current, what are we going to have first? Yep. So we're going to have plus R3IB minus R3IA, because that takes into account the total voltage drop of this guy. Yes? Well, we're assuming that the loop we're on is positive. So anything that's dealing with IB, we're going to assume is positive unless we come up to a negative voltage. Because we still don't know what direction the polarity of these guys are going to be. So we're making an assumption whatever loop we're on is positive, any opposing loop is going to be negative. But there could be times where we have current loops that come together that are going the same direction. Those guys are then going to add. Okay? R2IB, and we have to set that equal to 0. So with this one, it makes it nice because we don't have another voltage supply in the circuit. So now we need to combine these guys together to where we have the same variables. So let's start putting in some numbers with these guys. So we're going to jump back to loop A. These are original equations. So we have loop A. So we have negative 30 volts plus R1 was 330 ohms. So we have 330 IA plus R3, which was 330 IB. And then we minus, IA. And then we have the minus 330 IB equals 0. And now what we want to do is we want to put this into the format to solving for simultaneous equations, which means we want to combine everything together that has the same variable and move anything that doesn't have a variable to the other side of the equal sign. So this, we're going to combine our IAs together. We're going to combine all of our IBs together, and we're going to move anything that doesn't have a variable to the other side of the equal sign. We're just rearranging this so we can work with it. So we end up with 660 IA, because if we have 330 and we add 330 with the same variable, we just add them together, minus 330 IB. That is equal to 30. Everybody okay with that? Okay, where we get you lost, Simon? Okay. So now we have one variable, two variables equal to some value. Okay? So now what we need to do is we need to rewrite our second equation in the same format. So we get everything listed down. How many variables are we trying to solve for? 2. How many equations are we going to need? 2. And if you look, we don't have any other place we could get another equation except for maybe going all the way around the outside. But again, we're looking at the individual holes that we've created in our circuit. Okay, so we're going to switch over and do our equation for B. So we have, our equation is R3 times IB minus R3 times IA plus R2. So we put the values of what we know back into the equation. So we get 330 IB minus 330 IA. Takes care of the first two parts. Plus 170 IB equals 0. Then again, we simplify, combine everything down. So we're left with negative 330 IA plus 500 IB is equal to 0. Make sense? At this point, all we're doing is algebra. So the first part of our circuit is up here. This is the electronics portion. We're trying to figure out what do we need. We need our voltages to go all the way around. We're going to add all the voltage sources and voltage drops to give us a value of 0, essentially is what we're looking for. Then, once we have those formulas created, then it switches. This is all the electronics that we have to start with, is these two equations. Now it's just algebra. So now we take it, we plug in the values that we know, combine everything together, and get us two final equations where we have the variables equal to some value. And this, on their second equation, it's equal to 0. Now, the next step is we need to combine these guys together and start solving. So, yep, this is where we use our simultaneous equations. So I'm going to move our loop B down underneath this guy so we can combine them together. So we have minus 330 IA. We have plus 500 IB is equal to 0. Now, some of the things we learned last week is now we need to solve for this guy. These are going to be a little more complicated than the ones we did just in practice. Yeah, but the ideas are the same. So now we need to pick one of these variables to solve for so we can get it equal to the other side but opposite polarity. So as Max was saying, we can take this guy, multiply it by 2, so we can cancel out our IAs. So we multiply this whole bottom equation by 2. It's going to give us negative 660 IA plus 1000 IB is equal to 0. We combine these guys together. IAs will drop off just like we want them to. And then we get, so this guy, remember, we've now changed. So we've got 1000 IB minus 330 IB, 670 is equal to 30. We divide both sides by 670, and we get an IB value. Does this make sense as far as our units go? Because we have 30 volts divided by 670 ohms, which gives us current, which is what we're looking for. Yes. Okay. So now we take this value and we plug it back into one of our original equations or the equations we used to solve this step to solve for our other current. Because there's going to be times as we move up, we're going to have more than just two meshes. We can actually solve bridge circuits using mesh loops really quickly because of this. And we're just going to combine two sets of them together and simplify it down. So now let's take our 660 IA minus 330 IB, and we're going to substitute that value we just found for IB in. So we get 44.776 milliamps is equal to 30. And now we just simply solve for IA. So this value here, we have 660 IA subtracted by 14.776 is equal to 30. We add 14.776 to both sides. So we have 660 IA is equal to 44.776 volts. We divide both sides by 660 ohms. And IA comes out to be and now I have those values. So now that I have some values, I need to go back and look. First off, are they both positive or are they both negative or are they a mixture of in between? They're both positive. So both of them being positive means that these directions we picked are correct. So those are the directions that the current flows. Yes? Yeah. Oh, the 40. Yep. We're good there? Okay, Dylan?
So the directions we pick, it doesn't matter at all, but we just choose clockwise because then we need to know that we're starting the same way.
Mm-hmm. Yep. Yeah. So if by chance this B value had come up negative, we would just simply flip that around in our original circuit. Exactly. So now we have our currents. We're going to go back up. So now we need to solve for these guys. The other thing we'd be looking for, I forgot to write this down, IA and IB. So that's going to be part of the answers we look for. So now we know that we have those values. So IA was and IB was 44.776 milliamps. So now I got to go through and we're going to look and see how much current is actually flowing through each of these components. So we come back to R1. How much current is flowing through R1? 67.843. So we can find the voltage drop across R1 because now we have the current. How much current do we have flowing through R2? 44.776 milliamps. How much current do we have flowing through R3? A minus B. So now we get into the superposition part of things. We have one current going one direction. We have one current going the other direction. We're going to end up with a net between these two. And our final polarity is going to be based on which one is larger. So we end up with how much current going through R3? Say that one more time. In that direction. So which means our polarity of this guy is going to be like that. Because we switched polarities on this one, we're now flowing our currents from positive to negative. We're using conventional electron flow. Conventional current flow, I guess I should say. Whereas all the other ones, we're using electron current flow. The only difference is the point of view. What do we have moving? The positive charge or the negative charge? Now, that gives us voltages across all these guys. When we have our voltages and our currents, we can even solve power at this point without solving for the voltages. We use I squared R will give us the power as well. Okay, so what is our current total for this circuit then? Do we have any resistors on here that's our current total? Yeah, it's in this case, the current total is all the current going through R1, which is a 67.843. Does that still follow all of our series and parallel rules? Yeah, because we have the 23 plus the 44 gets us back to the 67. Okay, what's the voltage drop across R1? Okay, if we have 22.388 volts, how much voltage do we have across R3 and R2? Yep. Okay, we get that by taking the 22 minus from this guy, or we take it by the currents, individual currents, and we can double check those. 44.776 milliamps times 170 ohms should be 7.612 volts. Same thing with this one. The 23 milliamps times 200 or 330 should be 7.612 volts. And again, there's our double check to make sure that these guys, since these guys are in parallel, they have the same voltage. Everything matches up. We can get there either using our Kirchhoff's voltage loop. We can use the voltage divider, Ohm's law. Everything is still double checking out to give us the same values. I'll tell you what, it's annoying getting a haircut because you have to wear your masks right now. Masks fall into there, and then you're eating hair for the next 3 days because of it. They won't do beard cuts anymore. I'm going to trim this off when I get it home, but they won't do beard cuts at Great Clips now. Gotta love COVID. Okay. Any questions coming back to the beginning of this? You guys want to run through another one? Okay. Oh, I forgot to mention Norton, but we'll talk about him in a minute. Huh? Yeah, let's see. Thevenin's theorem was created in 1857, according to Wikipedia, so take that for what it's worth. Late 1800s, early 1900s was when Thevenin came out. That was his lifetime. Right. Like I said, that's why I said according to Wikipedia, very heavily asterisked. We actually, I side note, I had a teacher that relied on Wikipedia for information, and that's what they taught, and that was the gospel. Was the information was coming off of Wikipedia. So there was one time in class, we were given a quiz. We all bombed the quiz. We got on to Wikipedia. We found the answers after the quiz. Changed the answers in Wikipedia because anybody can add submissions to that. Changed it. Went back and said this isn't what we found. And he was like, "Well, what do you mean?" So we pulled up our article citing this. He pulled his article back up. Oh, I guess you're right. Changed everybody's grade. Did not learn anything in that damn class. We got tired of that. I won't mention. Oh no. Let's just say it was an electronics based class. No. Is not. I can neither confirm nor deny.
It's like poetry.
The guy knew his stuff as far as being a technician. He knew his stuff. He just wasn't very good at teaching. Yeah. I mean, the guy was smart with it. So this was years and years and years and years ago. This was when I first started taking electronics back in 2004. So, okay, voltage total is going to be 74 volts. R1 is 680 ohms. R2 is 150 ohms. And R3 is 110 ohms. Okay, so now we have our base circuit drawn. This is going to be referred to in the quiz as mesh loop analysis, 2 loops, 1 source. In a second, we'll go to 2 loops, 2 sources, and then we'll do 3 loops. Yeah. Yeah, I was going to say, because we can still do, that's the cool thing is like with Thevenin, it has its limitations. But once we get into like capacitors and AC, we can still do mesh analysis. Even with those guys, it just becomes a lot more complicated because now we're throwing imaginary numbers into the mix. Imaginary numbers is the heart and soul of what AC is. Yes. Okay. So the first thing is we have our circuit. We have to look at the negative space. Look at the holes in our circuit. Imagine we're zooming in on a piece of wire mesh. Okay? The circuit is the wire. We're looking at the space in between. So we have to establish our loops. Now in this circuit, we have 2 areas where we have holes, 2 loops. So we have loop 1, which is going to go from our source, from R1 to R3, and back to the source. Loop 2, or loop B in this case, is going to go through R3, through R2, and back to R3 again. Now, the next step. So now that we've established and we've drawn them, and again, we are assuming clockwise rotation on these. Now we're going to write out our Kirchhoff's voltage loop equations. So we're going to start in one point and go around and create this. So the first thing we run into is a negative 74 volts. The next thing we run into is R1. So we're going to have plus R1 IA. And then is that the only thing that we have going for R1? Yeah, that's the only current because there's no other circuit above here. So we have one current going through R1. We go down through R3. So we're going to add R3 times IA. Do we have anything else going through R3? Yes. We have IB. Go in the other direction. So we're going to minus R3 times IB. So just for kicks and giggles, let's change this. I know, I'm sorry. Okay, I'll put it back. We'll do another one where I flip that one just to show you guys for sure a negative loop. Then according to Kirchhoff, after we've taken the voltage sources and all the voltage drops of all the components, that has to equal 0. Because, yeah, nothing's left. Everything's been, all the energy we're putting into the circuit has been used. Okay, did we account for, that's the question, we just have to make sure. Did we account for every voltage drop in that loop? Yes.
Because there's the second current flow that goes the other direction.
Yeah.
There's a B circle in addition to the A circle.
Yep. So we're looking at all the voltage drops. R1 only has current A going through it. R3 has current B and current A going through it. And then the source is just by itself. So that's why here, and we're looking at everything from that point of view of the current we're working on. So we assume positive for anything with it, and if something is opposing it, we subtract that from our value. Then we go through, we need to solve for our KVL B for the other loop. So again, it doesn't matter where we start, just as long as we start at one point, make the full loop, and come back to it. So the first thing we run into, we'll start here, we run into what? R3. So we have R3 times IB, and we're assuming it's positive because we're dealing with IB. Then we have to subtract R3IA, because again, we still have the opposing current going through it. We come around, we run into R2, and what currents are going through R2? IB, that's it. So then this one is just added R2 IB. Because remember, this is Kirchhoff loop B, so it's from B's point of view, what is going on in the circuit. And that's one of the nice things too, is we don't have to make any assumptions other than the original loop. What direction is the current flowing? What direction is the voltage? We don't care. It will work itself out in the end. That's the real nice thing about mesh, is we just pick directions and go for it. We good there? Okay, so now that gives us our two equations. Now we want to go through and plug in all of our values into the equations and simplify them down as much as possible. So we'll come back to loop A. We have a negative 74 plus 680 times IA plus 110 IA minus 110 IB equal to 0. So all I did at this point is just substitute in the values that I know. We're going to solve for IA and IB. Once I have those, I'm going to combine everything together based on their variables. All the IAs I will lump together. All the IBs I'm going to lump together. Everything that doesn't have a variable, I'm going to move to the other side of the equal sign. So we have 790 IA minus 110 IB equal to 74. Where did what? Okay, you're good. I want to make sure everybody's following. I've had my daily Mountain Dew, so my brain's fully functional. Huh? Well, it's better than last week. Last week, my brain was not firing on all cylinders on Friday. It was a mess. Okay, so here is our first formula. Now we're going to do the same thing for loop B. So we have Kirchhoff's voltage loop. You're going to see this acronym a lot. KVL, KVL. It's Kirchhoff's voltage loop. So remember, you do a loop that has to equal 0. So we go to the second one, put the values in. We have 110 IB minus 110 IA plus 150 IB equal to 0. And again, on this one, I want to combine together all my IAs, combine all my IBs, and combine anything that doesn't have a variable, move that to the other side of the equal sign. Now, when I solve these, I do want to kind of put these in some sort of an order, so I'm going alphabetically. IA first, then IB, then when we get into it, IC will come next. You can put them in any order you want. Just make sure you put them all together when you're doing these, whatever order you pick an order and stay with it. So we end up with minus 110 IA plus 260 IB equals 0. Yes. In the end when we get a negative. Okay. Anybody have any questions getting to this point? And in the very end, yes. Everybody good to this point? Now we're going to take these and combine them together. So we have 790 IA minus 110 IB is equal to 74. And then we have a negative 110 IA plus 260 IB is equal to 0. This is also where these common multiples come into play. What are the factors? Because we could just brute force these guys together and get some ridiculously large numbers. And sometimes that works, and that's our only option. But we want to look for smaller values to multiply these two, because otherwise we're going to be looking with, we're going to have all sorts of kilo, mega things going into this, where we don't necessarily need that much. Of one of the variables. So either like 160 or 260. Sometimes it might just be to brute force them. Do what? Yeah. This one we're probably going to have to, brute force it. Let's see. Oh, this does have rectangular polar notation. Nice. Huh?
What's the cheat code?
Oh, I had to, so when we get into polar and rectangular notation with AC, we have to go back and forth. I didn't have an easy spot to do that, but now I just found it where, in the calculator where it's at. And of course, the instruction manual can't just say, here it is. So, yeah. So I created a personal program to solve that really fast for us while we're checking answers on these things. So, okay. This one we're probably just going to end up brute forcing. We'll just call it good. So we need to make one of these variables equal in magnitude, but opposite in polarity. So do we want to get rid of IA or IB first? And it doesn't really matter. Get rid of IA. So what we have to do is we have to multiply the top and the bottom by some value to get them equal. So in this case, I would multiply the top by 11, and I would multiply the bottom by 79. In this case, because both of them end in a 0, let's just chop that off to make our number smaller. And I think this value here is probably our least common multiple. So we multiply the whole thing, the top whole thing by 11. We multiply the bottom whole thing by 79, and we're going to get two new equations. So we get 790 times 11, 8690 IA. We have 110 times 11 minus 1210 IB, and that's equal to 814. So I'm multiplying the whole equation by 11 so we can get this. We know this value is going to be a negative 8690 IA. We have our 260 multiplied by 79, and we're already negative. That helps too. Then we have a plus 2540 IB. All that is equal to 0. Any questions here? All we're doing is trying to make one of the variables equal in polarity, or equal in magnitude, opposite in polarity. We simply add these guys together. IAs will completely fall out. And we're left with 2540 minus 1210. How much? Then that's equal to 814. We divide both sides by the 19330. IB equals, Jameson, I think you had it. It's close. Like I said, we're within 2 milliamps, but again, the closer I got was the 42.111. Right. Any questions about that? Yep, and we go back to one of our original equations. Oh, that would do it. Just swap this to 76 or something like that.
It was 896 when I
Oh, okay. Okay, so yeah, we plug that value in. So we have 790 IA minus 110 times the value we got for IB, which was 42,111. And here's the thing too. Whatever value we get, we leave it as that. So if we solve this guy and we get a negative 42, we take that negative 42, plug it into this equation, because this equation was built with that direction in mind. So like I said, it'll automatically take care of itself. That's going to be equal to 74. We then go through and solve for IA. So the 110 times 42, 111 milliamps is 4.632. Negative. We're going to add it to get it to the other side of the equals. We get 790 IA is equal to 78.632. We divide both sides by the 790. And IA is equal to what? Negative? Should be positive. Okay. Oh, because you typed in 709 instead of 790.
Oh.
Listdexia strikes again. Huh? So now we end up, we have an IA and an IB. They are both positive, which means our original assumptions were correct. Which is fine. If our assumptions are incorrect, we flip it, call it good, and solve the rest of the circuit. So IA, we have 99.534 milliamps. IB, we have is 42.111 milliamps. Go back up to our original circuit. Those guys are positive, so we don't have to flip those directions or do anything else with them. We put in the currents. 99.534 milliamps and 42.111 milliamps. And now with it, we go through and solve for our voltages. What current do we have going through R1? 99.534 milliamps, and that's it. There's no other loop or no other current path going through R1. So the voltage of R1 is this current times this resistance. What voltage do we get there? Yep. And if we have 67 volts, how much do we have being dropped across the rest of the circuit? And we can also verify that. What current do we have going through R2? IB, current B, the 42.111. That's going to get us to 6.316 volts. Now, here's the real question. How much current do we have going through R3? Yep, because we have 99 coming down. We have 42 coming back up. So we're going to end up with, get back here, current going in this direction. And how much? Which is going to give us a polarity of that. Okay, and then what's the voltage of R3? .316, which we find with that current and that resistance. I love it when Kirchhoff and Ohm work together. Do what? For loop A? Probably. Maybe some rounding in here is what I'm wondering. Okay, so what voltage did you get for this guy here? The 110 and the 4211 milliamps. It's all good. Volts. Because we're multiplying resistance and current together. Okay. And that is honestly the skinny of mesh analysis. We can do any number of loops at this point using the same one. So what we'll do is we'll let you guys go to break, and I'll get another circuit on here where we have a 2 power supply and 2 loops, and we'll solve it from there. A 20 loop one. That just starts getting into being a mess.